All right, over chapter 10 here, we've been talking about arcs and chords, and yesterday we introduced some properties. So if we kind of walk through this here, there we go. We talked about theorems 10.2 and 10.3 yesterday. Those are the brand new ones.
Nick Davis, Lorelei Cash, Zach Suby, Jason Lullabo, Lorna Whelan, come to the office, please.
Okay. These were basically talking about how an arc and a chord are directly related to each other. So we're talking about, if the chords are the same, the arcs are the same. That was one of them. Then the second one we talked about was a radius. If it's perpendicular to a chord, it will cut the chord into two equal pieces. And we talked about that. Those are the two we did yesterday. They didn't have any names to them. The goal today, and I said this yesterday, I want to do two more. 10.4. This one is the perfect converse of 10.3, so it'll say the words backwards. So instead of having the radius perpendicular to a chord, we'll have the chords already split into two equal pieces. Prove that the radius is actually perpendicular to it. And then the last one, 10.5, talks about pretty much the same idea that you're going to have pieces of a chord being equal. Prove that they're the same distance from the center of the circle. We'll talk about that. So there's actually two pieces of that one. So these are the two we're going to look at today. We had homework due yesterday, so if you didn't turn it in, I think everyone in this room did now. But make sure you're getting that turned in. That was the assignment we had yesterday. And remember, the note was the Ferris wheel had a radius of 24 feet. That was what we used that for the last four. I'll hand those back today if you want to make corrections and stuff. You'll have a little bit of time at the very end of class today, but I want to make sure that everyone gets a chance. Okay, this theorem you should already have, so don't scramble to write this down. I just want to do a quick review, like a 2-second review of what we talked about yesterday. Same circle or congruent circle, so it could be one circle or multiple circles. Two arcs are equal if their chords are the same, and vice versa. The chords are equal if the arcs are. So one of the problems I want to talk about today is one of the homework problems that eventually we'll see down the road. Was one of the problems was something about this, that they gave me 3x plus 2. This is a 2x minus 7, and the idea was, actually this is a 4x, I should say 4x, and the last step here was that these bubbles are the same. Maybe they say that these are 55 degrees, these arcs. Well, that just means if the arc measure is the same, that means the arc is the same distance. I know this is really weird that the book puts the angle for the arc on the outside, even though that's supposed to be on the inside of the circle here. This is supposed to be the 55. I find that always really funny that the book chooses to do that. But noting that the measures of the arc, they always call it measures of the arc, that's the angle that it is. If these are the same, then according to this theorem, the chords are the same length. So why this is useful, now I can take that problem, take the 3x plus 2, and set it directly equal to the 4x minus 7. And we can solve that. Because knowing that the arcs have the same measure, the same length, everything, that forces the two chords to be the same length. So I could subtract the 4x, subtract the 2, so 3x minus 4x, subtract the 2 to the other side, negative 7 minus 2 more. So this is a negative 1, that's a negative 9, divided by negative 1, and my x is a 9. And that makes both sticks equal to each other. And again, how do you know? Plug it back in, that's the only number for x that will actually make them the same length. So that's a shortcut. You can plug it back in. Questions with 10.2 and how we're going to use it today. We're going to get to more of this. This is the goal today, was to show you an example of that the homework's going to give you. And then after we're done with the notes today is maybe try a couple. See if you know how to do it. See if you know what to set equal. Do you know that they're equal? Maybe that's something that we'll talk about. Is there anything we could do on that problem? Maybe we couldn't. All right, questions, comments about it? Perfect. Moving on. All right, so next one. So again, that was my quick review of that theorem we did yesterday. 10.3, this is the one we also did yesterday. This one talked about if a diameter or radius is perpendicular to the chord, so it's at 90 degrees from the chord, it will cut the chord into two equal parts, and the arc is also cut into two equal parts. So maybe So this is the problem we did yesterday. So maybe they give me on this one that the arc, the measure of the arc from X to Y is let's say it's 102 degrees. Let's say that's what the arc is from X to Y. And let's go with the short way around. It's 102. They give me that, maybe they give me that CZ, that stick, is let's say it's a 4. And let's say that the distance from C to A is 5. And the question that they want to know is, what is the measure of arc X to B, and what is the length of XY? These are the things they want to know. That's a perfect homework problem. It's not overly difficult, but it's difficult enough that if you didn't know what it's giving you, it would be hard to set that problem up. Okay, so let's talk about this one. So the whole arc on the outside, this whole thing is 102. That's that arc measured. So according to this theorem, that if this radius is actually perpendicular to the chord, it will split this number in half. So what's half of 102? 51? That's what each of these arcs are going to be separately. That's 51 degrees, this is 51 degrees. That's the angle here, that type of thing. So this measure here is 51. That's the measure of an arc. It's the angle on the inside. Questions on the first part, how I got the 51. Again, knowing that it's perpendicular automatically cut that arc in half. So that was this part. The arc is bisected. So 102 split in pieces. Now, second part, this is the more difficult part. This is the part that most people struggle on. Is how do you find the length of X to Y? Because they gave me CZ, the C to Z is 4, and this whole stick over here is 5, C to A. Question?
Z to B is 1, right?
Okay, Z to B is 1. Okay, we have that. I agree with that. It is a 1. Maybe I should put that in a different spot. It's a little weird spot. It's a 1. That's how long that little piece is. Okay, but how do I find this stick? That's the goal. How do I find the length of the whole stick? Think we got it? Got some hands, please.
The arcs are equal, the length equal.
Okay, the arcs are equal, so the pieces, the chords, the parts of that chord would have to be the same. I agree with that, don't get me wrong. XZ is equal to YZ, I agree, but the problem is we don't have the lengths. So how do I find it? Using the numbers they gave me, I can actually find it. Say it again? No. So that's a great question. Is XY the same length as A to B? Answer is no. The only way that it would be is if XY actually passed through letter C. Because the minute you move a chord away from the center, so it's not a diameter anymore, you actually move this stick away from the center, the stick shortens. You're starting to see it. So if it's not going straight across and we move it, it's shortened up, so now it's a different length.
Could you make it in a triangle?
Oh, so, yeah, please.
Could you make it in a triangle?
There we go. All right, so now we're on here. You can make a triangle here, and now you'll have the numbers you need. Because I can move this 5. This 5 is the radius, C to A. That radius can be put anywhere. It can be put anywhere you want. So I can put the 5, so if you think about an arm on a clock, I think the best example somebody used yesterday was a spoke on a wheel, on a bicycle wheel. It's not changing size, it just moves. That spoke can go to a different spot. So now you have a triangle, which I thought was super, super, super clever. So now we can find this length right here, or maybe I'll pick a different letter of the alphabet. Let's call it W. I can find that length because it's a right triangle, and you can do Pythagorean Theorem, we can do SOHCAHTOA, We can do a lot of different things to this problem, and again, I'm going to stick with the Pythagorean theorem because I just made it the whole 102 thing. That's not probably accurate for this triangle, but because that doesn't look like 102. But how we can actually find that missing w is the Pythagorean theorem. That's probably the easiest way to do this problem. So let me draw this triangle over here. So we have the 4 is here, the 5 is here, and I'm trying to find w. These are the legs, these pieces. Those are the legs. This is the hypotenuse. So if you're going to do the Pythagorean theorem, a squared plus b squared equals c squared. That's the Pythagorean theorem. Right? We use that on right triangles when you're missing one of the walls. Well, the hypotenuse is always the letter c. That's just how that formula works. It's always the longest side. A and b are the other two walls, and I don't care which one's a and b. So that's 4 squared plus the w squared equals the 5 squared. And then what we do is we just solve for the missing wall. So you do a little bit of math here to actually figure it out. So setting this up, this is 4 squared is 16. That's w squared equals 5 squared is what, 25? We subtract the 16 across. 25 minus 16 is 9. And what's the square root of it? Yeah. Square root of 9, because that's how you get rid of the power 2. And you're absolutely right, this is a 3. So this w is 3, and that's the number I was looking for. But now I'm going to come back to what Nelson, you said earlier. The goal was to find the whole piece. What did you tell me earlier about these two sticks? Yeah, that was something you said earlier. Like the two pieces, xz and yz, they're the same length because the arcs are the same. So these two sticks are the same. So now that we know one of them is 3, we know this one's 3, that means the other one's 3, and what's the whole length? 6. And that's the number they're looking for. X, Y is 6. It's not overly difficult, but it's something like you probably have to see it once to go, okay, I know I can do that from now on. I understand how that works. Question?
Could you do the triangle on the bottom, like instead of top?
Yeah, it would have done the same thing. Yeah, exact same numbers, because you would have had the 4 here, you would have had the 5 going this way, it would have been the exact same math. Yeah, because they're the exact same triangle. Yep, great question. Now, if I would have had that correct number for the 51, that's not the correct number for 51 because I didn't know what the angle was, but we could potentially have used the angle because they gave me the angle, they gave me this whole 102 idea. I could have used half it, which was 51, and that angle is actually here or here. So let's say that was 51. And now I could potentially do the SOHCAHTOA stuff, sine, cosine, tangent, to figure out the missing wall and figure out the pieces, because I can do sine and cosine tangents, which is something we might practice a little more today and Monday. I don't think any of the problems require it, but it is always a potential you could use that to actually solve it. All right, questions on the whole Pythagorean theorem idea? Perfect. Okay, that's the number one go-to for these problems. Like that's what they kind of want you to do on most of them. All right. Okay, that's the quick review of those problems, and that was not quick. I took my sweet time on that one. Okay, 2 properties today. We have 10.4. Let me get rid of that. Man, this thing is slow. What is it doing? It's just taking the sweet time. What's the deal with this? Difficulties here, what's going on? Okay, so it's just showing up when it wants. This is weird. Okay, here's your next theorem. Hopefully it doesn't disappear in a second. Alright, so 10.4, this is our brand new one today. This is one that you will want to write down. The perpendicular bisector of a chord is, and it has to be, the diameter or radius of that circle. So the perpendicular bisector of a chord is the diameter of that chord, or of that circle, I should say. Hopefully the picture shows up. I don't understand what it's doing. perpendicular bisector of a chord has to be the diameter or the radius. So this is what we're trying to show. So this picture, I'm going to get rid of it here in a minute, but this is what we're trying to show. We're trying to prove this concept, that it has to be the radius or the diameter. That line, A to B, that line that I've drawn there is the only one that can do this. That can split xy in half perfectly and cut the arc in half. Like it's perfectly perpendicular and it's a bisector of that chord. And technically of the arc as well. So that's the goal. So the picture is going to go away. I'm going to get rid of it so we can actually talk about how to prove this thing. Because I don't want you to use the numbers there to actually show this. And I want to prove that this works. The problem is I don't know if the picture will go away here. I have a little technical difficulty here with this. Okay, is everyone good? Is everyone? Okay, Mullins, you good? Got it all right? Okay. Jen or Jane, you good? Okay. All right. All right. Let me get rid of the picture. Let's see if I can get rid of this here. Does it go away? Yeah. All right. We're back in business. Here we go. Okay. So let me draw the picture that I want. So we have a circle. And we have a chord. I can put the chord anywhere I want. Let's call this X and Y, just to stick with the same letters. And I'm going to draw this very bad on purpose. Just go with it. So this is going to be really, really, really bad. Okay. All right, let's call this point Z. All right. So what we know, and this, again, it's really bad. What we know is that this line, let's call this line WZ, we know that it is perpendicular to XY, because they gave me that. It is perpendicular, it's 90 degrees, and it bisects that chord. Now, I drew it really bad so that you don't assume anything. So this stick and this stick are equal. That's what bisecting means. That's our given. So line number one of this proof, the proof here, line number one is that we're actually given that XZ, or I should say XY, is perpendicular to WZ. So they are perpendicular to each other, and they are also equal. So XZ is equal to YZ. So we're given that. Okay, questions, comments, concerns about what we did there? Okay, now this is the part that's going to prove that my picture is really, really bad, which it looks terrible. We're going to pick a point down the road. I know that seems a little odd to say that, but we're going to pick a point down the road. Let's pick point P here. We're going to pick it down the road. I want to put point P in such a spot that it's on WZ, the perpendicular line. So you can put it anywhere you want. So we're going to draw this. So that's one of our constructions. I'm going to draw point P. All right, now why I did that is because whatever this distance is, I'm not even measuring, I just put a point on there. I can actually draw triangles in here. Does everyone agree with that? Okay, I can just draw those lines because it doesn't require any measurement. I didn't even care how long they were. So we picked point P. So this distance right here that, I just went, from Z up towards W. This distance from P to Z is actually the same stick in this triangle as that triangle. It's actually the shared wall. What is the shared wall called? It starts with an R. It's called the reflexive wall. Okay, so we have a reflexive wall here. So what I have is, if you actually look at the marks of my triangle, I actually have 3 marks in each triangle. 3 marks. So I can actually prove that the 2 triangles are actually equal to each other. So I can actually prove that triangle XZP is actually equal to the other triangle, which is YZP, which is unbelievable. Like when you're looking at a picture, there's like no way they're the same. They don't even look remotely close. But the markers say that they are, because the markers actually spell side, angle, side postulate. That's actually the reason why the two triangles are equal. Well, if the two triangles are equal, that forces these sticks to be the same. And the only way you can have sticks like that that are perfectly equal distant is if these are radii in that circle. That's the only way that they could be the same distance. They're going from the center to the outside. Or at least the line itself, I shouldn't say maybe they're not perfect radii, because they are equal segments though, these sticks, P to Y, P to X, they're equal in length. So that means at least this point P is actually on the actual diameter. Because if I go back to that really good drawing that I had up here earlier, a diameter, it doesn't matter where you draw lines from on a diameter to some point on the circle, these sticks are going to be the same length. Because the diameter is perfectly equally spaced from both halves of the circle. So if that's true, that's what we have here. So if I go back to that original picture, knowing that these triangles are equal and this is the actual diameter, then if I go back to this picture I showed up here earlier, what you actually have is this. Let's see if it'll actually appear. There it is. So you actually have this drawing that they're perpendicular, they're cut. So when I draw these lines, these actually ended up being the same length. And because of that whole reflexive wall, so the two triangles are equal. And so it actually forces this point to be on the diameter, and it could be a radius. It could be like the perfect center. Because that's the only way that you could be equal distance from X and Y, is if it's lying on the diameter that's right in between them. Because if C happens to move anywhere this way, then one of the sticks will be too long. So it is actually lying on the diameter. That's the definition of equidistant. The diameter and the radius are equidistant from each side of the circle they're having. Okay, questions? It's one of the, it's more of like a logic puzzle than it is actual theorem based. But again, it's based on perpendicular bisectors, equally spaced. All right. Oh, and by the way, that was called the converse of 10-3. That's taking the theorem that we did on Thursday, the one we did yesterday, and just flipping the words around. The words we had yesterday is if you had a diameter that was perpendicular to a chord, it bisected the chord. Well, this one says if you have a perpendicular and a bisector, the only way that that works is if it is a diameter, so it is the converse. Okay, 10-5, last one today. Here you go. Same circle or congruent circle, so it could be one picture or two pictures, but they have to have the same circle. Two chords are equal if and only if they're equidistant from the center. So, I'd like you to put below this one, I'd like you to put the word biconditional again. The word biconditional is that special word that we use that states a conditional statement, something that has an if and then in it. Biconditional can be written any ways, and the only reason why I can recognize it is because they use the words if and only if. It's a conditional statement that contains the words if and only if. Because it doesn't matter how you write the sentence. It's going to work no matter what. So I can start with the fact that the chords are equal, prove that they're equidistant from the center, or I can start with that chords are equidistant from the center, prove that they're the same length. So I'm just going to go one direction here. Again, I think this is on page 717 or something like that. That's the last thing today. So same circle or congruent circles. Two chords are congruent if they're equidistant from the center. So let me show you a picture here. So two chords are equal in length if they're equidistant from the center. So how you find distance from the center is you draw a line that is perpendicular. So this stick and this stick are equal. We're going to start with that fact. This would be the first way I want to go. I'm going to start with that these two chords, FG and JH, are the same space from L, the center point. So we know that LX and LY are the same length. prove that these sticks are actually the same length on that circle. Because again, L is the center. Well, this theorem is going to use a lot of what we did on 10.2, how that works. 10.2, or I should say 10.3, I should say, that when you draw perpendiculars from the center, it bisects chords. So we're going to actually be bisecting chords here. But we're going to use that fact here in a little bit. Okay, so right now what we have is LX and LY are the same. That's what we're doing. Okay, second, we have the perpendicular, we have that angle. I'm going to draw a line from L to F and L to G, L to J, L to H. What are these lines called? What are those lines called? From L, that L is the center.
Radius?
Yeah, they're radii, right? The radius. They're all the same length. So on this picture, all these radii have the same length to them. So now that I know that, I can actually prove that all four triangles are actually equal to each other, which is absolutely insane. Like all four of them, all four triangles. Because if you look, they're all right triangles, they all have right angles in them, you can see that. They all have a leg marked, and they all have the hypotenuse marked. The hypotenuse is the longest side of those triangles. The hypotenuse happens to be the radii in each one. And we said the radii are all the same length, right? So in each one, I can use the L or the HL theorem to actually prove that all four triangles are equal. Well, if all four triangles are equal, then that forces these pieces to all be the same. Because those are just pieces of those triangles, right? So if the triangles are equal, because of the HL, hypotenuse leg theorem, then the third walls are also matching. And when you add those third walls together, it makes the entire chord. So I can actually prove the triangles are equal, so that forces Fx to be equal to Xg, which is equal to Yj, which is equal to Yh. So we can actually prove that all four of these are the same stick, and if you add the pieces together, yes, they still make equal parts. That you can add equal things together, and they're still equal. It's like the idea if you picked, bless you, let's say I had the number like, I know this is going to be really weird. You pick the number 7. You agree that 7 is equal to 7. If you add the same number to both sides are still equal to each other. So if I just make up another number, let's say like 41. I can add 41 to both sides, and both sides would still be equal. As long as you add the same number to both sides, it's still balanced. Well, that's what I'm doing here. So if I know that all four of these are equal, I can just magically add equal parts to both sides, and they're still equal to each other, right? That, the sticks are still the same because I added equal parts to both sides. Well, that's how you actually prove that the chords are the same length. Because all four parts are equal, so you can add any parts that you want because they're all four equal to each other, and you can make the entire chord. So it's actually using segment addition. I can add segments together to make longer segments. But they're all equal. So the spacing's the same, the chords are the same. That picture's getting terrible looking. Alright, well that's it for today. That's all I want to get to. I was going to do a couple more examples, but I want to give you a little bit of time at the end of the day. We have about 5 minutes left here. Okay. I'm going to hand back some papers. You want to make some fixes, you can do that. So I'll give you a little bit of time here at the very end. But again, you have about 5-6 minutes left here. I want to give you some papers. Make some fixes, turn them back in. You guys know the drill.